Welcome back to part 2. Let's go back one slide because I realized I made a little mistake there. So here, this R value of negative 0.757, this is our correlation coefficient. I accidentally called it the coefficient of determination. That's actually R squared, and we'll get to that in just a couple slides. So the R value is our correlation coefficient, and here we found it's negative 0.757. Let's start part 2 now. So that correlation coefficient, or the R value, specifically it's Pearson's product moment correlation coefficient, it ranges from -1 to 1. So -1 and 1 would both be a perfect linear relationship, but they would be in opposite directions. So 1 would be a perfect positive relationship, and -1 would be a perfect negative relationship. So here are some examples of how that value changes, the correlation coefficient changes, as your data is perfectly linear. So here, for example, we can see a perfect linear relationship. So you can see how that makes a perfect straight line. So your correlation coefficient will be 1. It has a positive slope, so it's +1. These data over here, that's also a perfect linear relationship, better than the line I drew. But it has a negative slope, so it's a perfect -1 relationship. Then what you can see is as your data become more cloud-like, if it is a perfect cloud, then you are going to have a correlation coefficient of 0. There is no linear relationship between these two variables. And what we get more often in research is, something in the middle. So the one we just looked at, it was close to -0.8. So you could visually see a relationship there, but of course, people aren't robots. There's variability to everything we do. So you're unlikely to get these perfect relationships, but there will be, of course, some variability to them. The question is, how much variability, and is that still a significant or a meaningful relationship? So here you can see these are all examples of perfect relationships between the two variables. The 3 on this side all have a positive slope, so they are a correlation coefficient of 1. These 3 all have negative slopes, so they have a correlation coefficient of -1. And if it's a perfectly horizontal line, well, that line has no slope, so you actually can't calculate a correlation coefficient from that. Now, correlation coefficients, it's important to remember that we're only looking for a linear relationship, so a straight line relationship between our two variables. And there could easily be another sort of relationship that the correlation won't pick up. So you could have an exponential relationship. Some of these relationships down here are quite strange, but if you plot your data, there's obviously something going on there, but your correlation would give you a score of 0 because it's not a linear relationship. So it's important to plot your data and to see, is that relationship linear? Should we be analyzing it with a correlation coefficient? And if it's not linear, if it's something more complex like this, this circle over here, then you don't want to say, hey, there's no linear relationship and mislead people into thinking that there's no relationship when there's a strong relationship. It's just not linear. Next up, here, let me move my window so we can see this. The nice thing about correlations, unlike a t-test or ANOVA, is the measure of effect size is built right into your correlation coefficient. So we don't need to calculate a Cohen's d, eta squared or partial eta squared. That value r is already a measure of effect size. So a correlation, that r tells us two things. The strength of that relationship, so the closer it is to 1 or -1, the stronger the relationship. And if it's positive or negative, tells us the direction of that relationship. How are these two variables changing with respect to each other? And we do have some conventional measures that are used. So an R value of +1 or -0.1, so absolute value of the R of about 0.1 is a small relationship. A medium effect size is 0.3 and a large effect size is 0.7. So our correlation coefficient here was almost 0.8, so that is a large effect size, or probably if we wanted to extrapolate, we could say that's a very large effect size. I was actually a bit surprised at the strength of the relationship between attendance and grade. I expected a relationship, it makes sense, but I didn't know it was going to be that strong of an effect. That brings us to r squared. This is one I mistakenly referred to earlier. R squared is another measure of effect size, and it's the coefficient of determination. And r squared, the calculation for it is very simple. You take your r value, in this case it was negative 0.757, and you multiply it by itself. So the correlation coefficient r times the correlation coefficient r gives you your r squared. Now by convention, the coefficient of determination is a capital R, and the correlation coefficient is a lowercase r. So r squared, if you think about the math behind this, it's going to range from 0 to 1. So it no longer tells us about the direction of the relationship. It's always going to be positive, but it tells us about the amount of shared variance between your two variables. So the coefficient of determination measures the proportion of variance shared by our two variables. So if you have an r squared of 0, that means there's no shared variance between these two variables. There's no linear relationship at all. And if you get a value of 1, that means 100% of the variance is shared between these two variables. It's a perfect linear relationship. So in this case, our coefficient of determination was about 0.6. So if you multiply that by 100 to get a percentage, that means about 60% of the variance, or 57.3% of the variance, was shared between our two variables. I'll move my picture here. There we go. So the variance, if you think of each of the variances in these variables kind of like a Venn diagram, 60% of that variance overlaps. So there's a high amount of variance that is common to these two variables. So r and r squared can both be used as measures of effect size. When you look at r, you kind of have to remember our typical guidelines for the effect size. R squared people like to use because you don't have to remember that, 0.1 is small, 0.3 is medium, because it directly tells you about the amount of shared variance. So as I'm sure you've heard before, correlation does not imply causation. So if we look at this graph here, someone is coming in and saying, hey, there's no evidence that cell phones cause cancer. So they're looking at some data here, and one evidence for this, I guess, would be that cancer was around before cell phones, and as cell phone use has gone up, cancer incident has remained stable. And the funny part here, why am I explaining a joke? I don't know. Okay, let's just run with it. So what you could conclude from this relationship is that cell phones don't cause cancer, but the other thing, the humorous part to conclude, is that, well, maybe cancer causes cell phone use, because as cancer increased, all of a sudden, cell phones appeared. So when we look at a correlation, it suggests a relationship, but we can't say it's a causal relationship. To know if one variable affects the other, so does variable A cause B, or does variable B cause A? Well, that would take an experimental study where we manipulate those variables. So we have to be careful when we look at correlations and never imply or definitely don't conclude a causal relationship. If we go back a few slides, let's look at our data. We're jumping back a lot here. When we think about a causal relationship between your attendance and grade, it could really be in either direction. It could be that, you stop going to class, so your attendances increase, your absences increase, and that is what causes your grade to decrease. That's one direction to the relationship. But it could also be that, well, maybe you did very poorly on test one, and getting that bad feedback then caused you to stop going to class. And we don't know. We know there's a relationship here, but we don't know which direction it is. And it may also, it might not be that simple. There could be a third variable that could explain this relationship. Let's jump forward and talk about that. So to make this point a little more humorous, let's look at this data set here. And here we're looking at the relationship between ice cream production and the number of drowning deaths. And when we look at these data, it looks like there's a pretty strong linear relationship. I don't have the exact correlation here, but it looks like we have a positive relationship between these two variables. So is it that as people drown more, that us survivors are depressed, so we eat more ice cream? That could be one direction to the relationship. Or is it that, as we eat more ice cream, we then go swimming, and with a full stomach, the ice cream makes us drown? I don't know, something silly like that. We don't know. It could be either, and more likely, especially in this case, it's neither. There could be a third variable, or it could be just a sporadic, indirect relationship that causes the correlation. So for that first idea of a third variable, I think we can explain this relationship here with a third variable, and that is, hot weather. So as the weather outside gets hotter, that leads to two things. One, we go swimming more, and two, we eat more ice cream. So more ice cream has to be produced to meet the demand. And of course, when people are swimming more, compared to winter, you'll then, of course, have some drownings. So there's probably no relationship, no direct relationship between drowning deaths and ice cream production. We could probably explain it through this third variable of hot weather. Sometimes we see other correlations that are even more far-fetched, where there's probably not even a third variable to explain them. It's just some sort of indirect relationship that occurs. And we need to think about this when we interpret our data, especially if you're running many correlations. If you have a giant data set, you're correlating everything with everything else, which is not advisable, you'll probably find some significant relationships. Then you need to ask yourself, are these maybe causal relationships? If you want to investigate that, you have to run an experiment and manipulate those factors. Is there a third variable causing these? Or is this some sort of indirect relationship that's really meaningless? And on that last note of indirect relationships, there's a great website. You can see the link there. It's all about spurious correlations. This is a bit older now. I think it was actually done back in 2009. And the creator, Tyler, what they did is they got publicly available data, so mass data sets, and then just told their computer to try correlating everything with everything else, and they looked at which correlations came out, and a lot of these are very strong correlations, but they're likely spurious or indirect in nature. So the first one here, the per capita cheese consumption has a strong linear relationship with the number of people who died by becoming tangled in their bed sheets. And those probably don't have a direct relationship. It's a spurious correlation. It's an indirect relationship. But here you can see the correlation value. The correlation coefficient is 0.95. And if you look at the data, you can see that's a really nice linear relationship. Here's the second one. I think these all three are food themes. I must have been hungry when I made these. So the per capita consumption of mozzarella cheese is correlated with civil engineering doctorates awarded. And of course, those two things are very unlikely to have a causal or third variable relationship. It's a spurious correlation. It's some sort of indirect relationship that we found by chance after correlating many different data points with other data points. Third one, we can see here the divorce rate in Maine has a pretty good linear relationship, a coefficient, not a coefficient of determination, but a correlation coefficient of 0.99. So almost a perfect linear relationship of divorce rate being related to the per capita consumption of margarine. And that one just makes sense, because the more margarine you eat, the more likely you are to get divorced. We'll see another one of these spurious correlations. We'll actually use, I've pulled the data out for your assignment. All right, so that is the end of part 2.